Hi, everybody. Before we actually get into this speech, I wanted to give a quick explanation. Dr. Zage and Dolores Zage are supposed to be up here with me. They sent me an email on Friday saying, hey, by the way, we're not showing up. I was like, well, okay. I was like, well, why aren't you showing up? It's like, oh, well, our son's got to move to Sandia National Lab, so we're going to help him. You know, DEFCON's not a big thing, so you can handle it. You're a grad student. So I was like, okay, well. So basically, I added their email addresses at the last minute, so just, you know, that was the advice I got from some of the DEFCON goons. So, you know, you guys want to email them, whatever, any of this stuff. But also, then they sent me yesterday, I was like, well, you know, this is based on 20 years of metrics research, and I did a lot of the security side of things, but not as much the metrics side of things. So I said, so how am I supposed to, you know, really do a good job explaining this? So they sent me their research papers. So then I was like, okay, 20 years of research papers. So I went through what I could, took notes, and, you know, basically get through the speech the best as we can and answer your questions to the best of my ability. I have a pretty good understanding, but like I said, I would have preferred for them to be up here with me. But, you know, the speech must go on. So the presentation outline, we're going to quick overview of S-squared ERC. It used to be SERC. It used to be the Software Engineering Research Center. Now it's the Security and Software Engineering Research Center. And then, you know, get on to the actual metrics and the vulnerability analysis. Let me get through these. I've got some notes. This is going to be the first DEFCON speech that I actually have to take notes to. So basically, it's a National Science Foundation, University Cooperative Research Center that, you know, it's funded by them, has a ton of universities, 10 plus, 50 researchers. It's all collaborative. We have projects, you know, any company or you have government agencies, everybody else sponsors their projects, sponsors us to do research projects for them. The participating universities, I'm not going to read them off to you. You can see them. They're in the slides. They're on the CD. We have a ton of industrial affiliates. This is not really stuff that I care about as much. Okay, then here's the design metrics timeline. Like I said, it's about 20 years of metrics research. So it started in 1986. And I believe it all came out of Purdue University. Is Dr. Wayne Zage, his baby. From what I could tell, the first research paper they sent me was from Purdue, so I'm guessing that's where he did this research at. Let's go ahead. Okay, I guess they were going to click through, and this is really annoying. Okay, they got a Alexander Schwarzkopf Award for their research. Basically, I'm guessing they wanted that in here to say, hey, it's credible. Like I said, this is their content, so I have to basically stumble through some of it. Okay, here's some of the, actually get to the good stuff. Overview of the design metrics, D sub E, D sub I. D sub E is an external view of design complexity, and D sub I is going to be the internal view of design complexity, which is, you know, that's pretty much when we're talking about faults in software. The more complex something gets, the more error prone it's going to be. So this is basically when they started this stuff, it's all goes back to, it was all just reliability. This is, you know, 20 years ago, nobody really seemed to care about security. But they did care, you know, they didn't want their software crashing, or, you know, if you have navigation system or whatever else, you know, you don't want that thing going down. So it was all, reliability was the focus for software when this research started. We look for outliers. Pretty much, you know, you have these modules that come up as very error prone, fault prone. That's what we're looking for. And there's all the people that have funded us. This actual project to actually take the reliability metrics and apply them to security was funded by Army Research Labs. So let's get through. We've computed metrics on university-based projects, Computer Science Corporation, Stanfin, systems from Army Research Labs, Harris's Rock Project, Magnavox, PBX System, Northrop Grumman. The stuff that I was actually part of is all the open source projects. So I didn't do metrics on these. These are Wayne and Dolores. Now, on the results for the actual reliability metrics, they have correctly identified in the worst case scenario, 76% of the defect-prone modules. Now that's in the worst case scenario. That means, you know, the worst time you ran it was 76. It's almost always higher than that. Generally closer to 80 or 90%. So now we're getting into some definitions of our external metric D sub E. You can see D sub E is inflows times outflows plus fan in and fan out. I'm going to go ahead and go over that nomenclature because I'm not sure how standard it is. That's what I got from their papers. Inflows is basically any data coming into a module. It doesn't matter, like it could be parameter passing, global data, reading a file. Any data coming in is going to be an inflow. So then an outflow is any data coming out of a module. So let's say like a file change, if your module writes to a file, that would actually be considered an outflow. Or it could be passing something out. Anything that's coming out of that module is outflow. Fan in are going to be the modules that actually use the module focus. By module focus, it's the module you're trying to run primitives on. And I guess I should, just to make sure, define what I mean by module is any addressable, callable piece of code. Because since, on this reliability metrics, it's not limited to C or Java or Ada or Perl or any other language. So, because the languages are so different, we're just say a module is a callable piece of code. So anytime I say module in this speech, that's what I'm referring to. So then fan in, like I said, is modules, account of the modules that use the module focus. So if you're saying we want to detect reliability in this module, how many modules call it? So that would be your fan in. Then your fan out would be how many modules does it call? So then as you can see here, we've got basically it's actually kind of simple. Once you have it all defined, you have 2 plus 2 plus 3 times, and then you get your result is 23. So let's go ahead and we're going to break that down with each part: inflows, outflows, fan in, fan out. Then we have an internal metric, which is, let's get through here. That's actually a measure of the internal complexity of a module. And what the equation for that is, you have your central calls, your data structure manipulations, and your input-output. Now, W1, W2, W3, that's something I was confused about, went back to the research papers. All those is weight. So if you wanted to give more focus to data structure manipulations, then you could give W2 a weight of 2 or a weight of 3. So for all of our metrics, unless if the actual, the people funding us to run metrics request a specific weight, W1, W2, W3 is always 1. Army Research Labs, the SMART project, the values of W1, W2, W3 were always 1. Just to make that clear. So then, sorry guys. So extending design metrics technology to a software security engineering process, really what we're trying to say is, like, how do these actually apply, reliability metrics to security? And looking at defect rates, a deployed software package of 1 million lines of code has 6,000 defects. So let's say if we assumed 1% of those defects are security vulnerabilities, there are at least 60 different opportunities for someone to attack a system that is a million lines of code. So really what we're saying is that, and I'll get into this a little bit later, is that the reliability faults, you're going to have security faults within those. So the majority is going to be, you have a ton of reliability faults, then a small number of those will actually be actual security faults. Let's get through here, and this is where I'm talking there. So you have your defects, and within that, some of that's actually exploitable, and that's kind of what we set out to prove when we did this project for the Army, is to say that, yeah, these metrics that we've been using, proven over 20 years for reliability, can actually find security faults. So when you look at the parallels, you have a fault-prone component. It's likely to contain faults. On the security side, vulnerability-prone component, which is likely to contain vulnerabilities. A failure-prone component is probably going to have failures in the field. That's the things you really want to get, because that means your stuff is going to crash. So when we look at the security side, we say, well, then you're going to have attack-prone components, which means it's actually likely to get attacked in the field. And when we actually did an analysis on a large commercial telecommunications system, we found that the presence of security faults did correlate strongly with the presence of the general category of reliability faults. So when we saw that was kind of before this project, and that really led us to believe, well, we can use these metrics that have been used for stability and actually take our error-prone modules are most likely going to be vulnerability-prone. So our project objectives, we wanted to investigate the overlap, like I was saying, and see how much overlap is there, and will our system actually find vulnerable pieces of code. There's our systems that we did: Firefox, OpenSolaris, OpenSSH, and Drupal. And Apache. I don't know why I didn't have that on there. So pretty much we considered it would be really good if 50% of the components contained documented vulnerabilities would be identified. And what I mean by that is you have like CWEs or CVEs. Basically everybody here that does security knows, you have patches, and so you actually have the stuff get reported for the most part. So you have reported vulnerabilities. So what we did is gather all those reported vulnerabilities on these products and then run the metrics on those specific versions and say, okay, well, were we actually able to identify these, vulnerability prone components? So that's the whole process basically is you take your system, then you build a list of all your vulnerabilities, what version of the code it was, and this is where I actually, my big part in this research project was I would take a report of a vulnerability and then say, okay, well, what is actually causing that vulnerability? What's the actual vulnerable piece of code? Because that's really what you need to know, because when you're doing your metrics and it gives you a specific module, you have to make sure you have to know where the vulnerabilities was, or else you can't say if it actually identified it or not. I mean, if it says, hey, Apache has a buffer overflow, but doesn't tell you exactly what module the buffer overflows in, that doesn't do you any good. So that was really my part, was to find exactly where those vulnerabilities were. So then when they run the metrics code, we could then say, okay, well the metrics actually identify all these. So there we have, these are our CWEs, how many that we'd collected for the different versions. We did OpenSolaris. I'm not sure what the version was on that. Firefox, we had 2.001, 2.002, 2.005, OpenSSH, HTTPD, which I believe will have the version numbers in just a second. So everybody knows what Apache is. I don't really need to go over this. For the vulnerabilities on version 1.3.1, you had 144 files, 8 vulnerabilities identified. With the metrics, we actually had 87.5%, or 7 out of 8 vulnerable modules were identified in the top 10%, which is a huge win for us, because that's saying, if you are a code auditor and you want to know where to look, then that's a huge win to tell you, if it says, hey, this is the top 10%, and that's actually where the vulnerabilities were, then that's pretty good. I mean, at least, in my opinion. So there's a graph of some of the output. It shows, hey, these are the modules that are likely to be vulnerability prone. OpenSolaris, I think everybody knows what that is. So we had 22,600 files, 23 module updates from vulnerabilities, totaling 37 changes. 5 is the largest number of changes on one module. So we wanted to identify 23 modules out of 22,600 modules in files, which is approximately 1 in 10,000. So yeah, pretty tricky. So Dolores wrote some code for this that she calls her, her divide and conquer. And let's see. There we go. So we actually got, when she got that code to work and pick apart, because I guess there's a lot of weird stuff in there that was messing up her preprocessor engine, but once she got that working, we had 60%, or 3 out of 5 vulnerable modules, and 69%, or 9 out of 13 changes were identified, which is pretty good. Not as good as all of our, the reliability numbers, but for a system that complex with that much code, still felt it was, pretty good results. Firefox, again, another